Hello. In this video, we want to look at the definition of complex numbers, and then we're going to simplify some radicals. So a complex number, or the standard form of a complex number, is a plus bi, where I is the square root of -1 and I squared is -1. And the reason that this comes about, at least not historically, but the way that we like to talk about it for now, is x squared equals -1. What's the solution to that? Well, really, there are only two possibilities. It's either -1 or +1 in the real numbers. So what is -1 squared? Well, -1 squared is -1 times -1, which gives us +1. And unfortunately, that's not -1. And if we square 1, that also gives us +1. So when you square something, it's always positive in the real numbers, or at least non-negative. So the problem is that in the real numbers, there is no solution to this particular equation. So as a result, we have to ask ourselves, well, what can we do to, actually solve this? And I forget exactly when it happened, but some crazy mathematician decided to say, well, let's define a variable I such that it's the square root of -1. And when you have that, if you plug that into this equation, and you say square root of -1 squared, the square root and square cancel each other, and you're just left with -1 over here, and that's equal to I. So basically, notice that if you say I equals the square root of -1, and then you square both sides, you get I squared here is equal to the square root and square cancel each other, leaving you with -1. And notice that this is in fact this form. That's the reason why I is in fact a solution to that. Wonderful. Now let's talk about the actual standard form. The standard form is a plus bi. A and b are real numbers, and real numbers are pretty much any number you've ever seen. 0, 5, -15, 3/4, 1/2, square root of 2, square root of 5, pi, any of those are all just real numbers, okay? But every single real number can be turned into a complex number by having an I in there somewhere. Now, technically, we have two different kinds of complex numbers, well, three different kinds of complex numbers. If you have just an A, in other words, just the real part there. By the way, A is called the real part, and the B is called the imaginary part. So just an A, that's called a real number. Just a B, that's called an imaginary number. But both a real number and an imaginary number they're both complex numbers. So every number that you've ever seen has been, in fact, a complex number. It's just a complex number with an imaginary part of 0. That's all it is. All right. With this information, we're going to go ahead and simplify some radicals. Okay. So, a radical is simplified when the radicand contains no perfect square factors. And let's go ahead and talk about what a radical is. A radical is this symbol. So that right there is in fact a radical. Now, the term radicand is whatever's underneath the radical. And every single radical has a number right there, and that is called the index. Now, notice that for all of these, there is no index written. When an index is not written, it's a 2. It's the reason we call it a square root. If you have a 3 right there, it's called a cube root. A 4 is a 4th root, a 5 is a 5th root, and so on and so forth. Now, a radical is simplified when the radicand contains no perfect square factors. And the instructions we have here are to simplify each radical exactly or state that it cannot be simplified. Okay, so first of all, square root of 36, I hope you know, is 6. And the reason for that is if you take 36 Notice that I can write it into factors of 6 and 6. But notice that 6 and 6 is just 6 squared, right? So square root of 36 should give us 6. That's really all a square root asks us, is what number squared, because that's the index, gives us the radicand. That's what a radical is asking us. Now, let's go to b here. Now, b is the square root of 12. Square root of 12 is a little bit different, because if you tried to do a prime factorization of 12, well, what gives you 12? Well, you're probably going to tell me 6 and 2 and 3 and 4, but that's not really what I wanted. All I want is one of those two. If you tell me 6 and 2, that's fine. Or if you tell me 3 and 4, that's fine. Either way is fine, or 2 and 6 and 4 and 3, doesn't matter. But notice that this 2 here is prime. And in a prime factorization tree, any branch that has a prime is done. It doesn't go any further. But anything that is not prime, called a composite number, continues a little bit further. What two numbers gives me 6? Well, it's 2 and 3. And notice now that at the ends of each of these branches, we have prime numbers. Now, prime numbers are just numbers where where the factors are only 1 and itself. We don't consider 1, but it's basically, it is its own factor. And that's it, no others. So 2, 3, and 2. So here's the thing. With a square root, there is an understood 2 right there. Now, what that's telling me is I want to look for pairs of primes. So I'm going to go ahead and look and see, oh, there's a pair of 2's there. So I'm going to go ahead and circle those. This 3 does not have another pair to go along with it. So what I'm going to do is I'm going to multiply everything that is circled together. So 2 times 2 is 4. And everything that's not circled, I'm going to multiply together. 3 times, well, there's nothing else, so just 3. And what this means is that you want to think of the square root of 12 as the square root of 4 times 3. And the reason that this helps us is because the square root of a times b is the same thing as the square root of a times the square root of b. And as a result, this allows us to say, hey, look, that right there is a perfect square. It's guaranteed to be a perfect square, but we should know that 4 is a perfect square already. So let's go ahead and break this up into 2 separate factors as the square root of 4 times the square root of 3. And then just ask ourselves, what's the square root of 4? Well, the square root of 4 is just 2. And then square root of 3, you just leave as the square root of 3. This will never be able to be simplified ever. And there you go. We're done with that one. As for C, the square root of 15, the only thing that makes up 15 are 3 and 5, or 5 and 3. But notice that 3 is prime, 5 is prime. There are no pairs within this. So therefore, this cannot be simplified. In other words, square root of 15 is its simplified form. And as for letter D is a little bit different because it's a fraction. So let's go ahead and get another rule here. The square root of a over b is the same thing as the square root of a over the square root of b. In other words, the radical of a fraction is the fraction of the radicals. So it's going to be the square root of the top divided by the square root of the bottom. And if you notice, 25 and 16 are both perfect squares already. So square root of 25 is 5, and the square root of 16 is 4. And there's your answer. Alrighty. Well, I believe that is it for this particular example. So I'll see you in the next one. Have fun.